Okay, there are two primary advantages with using the traditional or school method. The first primary advantage is related to the reduction of the minimum processing time that it takes to solve a question. This allows you to do certain multiplications, especially medium sized and smaller multiplications, faster than if you tried to use cross multiplication. For example, if you were given a 2 by 2 multiplication question, not many people are going to actually apply the cross multiplication process to that. They can simply use school method and do it quickly. If you're experienced and practiced using the school method, that same observation can be extended to larger multiplications. The second advantage of the school method is working from left to right. This has a variety of benefits. First of all, if you're in a situation where you're expected to answer from left to right and you cannot write down the answer a digit at a time or type the answer a digit at a time, then using school method is going to be critical. Second of all, solving from left to right allows you to estimate the answer much more quickly. If you don't need the full answer, then working from left to right would be preferable. Third of all, if you need to remember the result of the multiplication and continue working with it, and you can't write it down, working from left to right is going to allow your brain to remember the answer much more efficiently than if you were trying to do a digit by digit calculation, especially if you're going from right to left. The advantage of cross multiplication is somewhat obvious. You can work one digit by digit. You can break down the question into very manageable, easy calculations. Only solve a digit at a time, write or type the answer as you go. No need to retain information, no need to do complicated calculations, and yet you can solve a large multiplication question and rather quickly. Okay, so I'm going to take a look at how the different approaches result in deconstructing a 5 by 5 question. For cross multiplication, if you're doing cross multiplication, you're going to end up with 25 1 by 1 multiplications and 16 additions. They're usually going to be 2 digit by 2 digit. On occasion, you could end up into the over 100, and often regularly they will be a single digit. But so 25 1 by 1 multiplications, 16 additions. When you're doing school method, you are only deconstructing one of the numbers, and the result is 5 5 by 1 multiplications and 4 additions of 5-digit numbers. So how does that different deconstruction of the question manifest itself in different times? So we're going to try to model it really quickly. For cross multiplication, my best estimate for how long it takes to react to seeing a 1 by 1 multiplication and for the time to pop in your head, 0.1 seconds. Obviously that is an estimate. For top non-Soroban addition competitors like myself, adding two digit numbers can be done at 0.2 seconds. Maybe you can get a little bit faster, but that tends to be a very, very good score for a non-Soroban competitor. So if we're going to take the framework from the last slide, and a 5 by 5 multiplication is broken up into 25 1 by 1 multiplications and 16 additions of 2-digit numbers, we would estimate a 5 by 5 time of 5.7 seconds. This is very much in line with the top 5 by 5 times for Western competitors especially. I do not recall what Mark's official record was, but it's very close to 5 seconds. Unofficially, you can get lucky. You can push maybe a little bit faster than 0.1 or 0.2 for the two different components, but you're unlikely to be able to beat 5.7 seconds by a significant margin. Using school method, however, produces a different calculation. We have 5 by 1 multiplications and then the addition of 4 additions of 5-digit numbers. So it's a little bit difficult to estimate this. I suspect a 5 by 1 multiplication from my attempts to estimate it for myself would likely be around 0.5 seconds. And we can estimate rather well how long it takes a top Japanese competitor to add 20 digits and the general rule is it's 20 digits per second. So we have 3.5 seconds as a estimate for their time in 5 by 5 multiplication, which happens to be quite accurate for the top times for Japanese competitors. Again, like in the second bullet point, you can push a little bit faster than the model would estimate. We see in the video that was posted and the first multiplication tutorial that the appears to be the record time for a Japanese competition is 2.7 seconds. But again, you can get lucky, and you can with a lot of practice and work push a little bit faster than what this model suggests. So if you're not quite convinced that the model is an accurate way of assessing the performances, let's apply it to an 8 by 8. And for cross multiplication, you're now going to have 64 1 by 1 multiplications and 49 two-digit additions. Using the same average times as before, we get an estimate of 16.2 seconds, which actually happens to be the old official record time for Mark. For the school method, we're going to do 8 by 1s and then the corresponding additions. So again, it's really difficult to estimate an 8 by 1 multiplication. I'm using 0.8 seconds. That would give us 9.2 seconds as a model for a Japanese school method time for 8 by 8, which does appear to be quite consistent with the videos that were shown in the first tutorial video, as well as those can be found online. 9.2 seconds does appear to be what an elite, roughly an elite time for a Japanese competitor doing 8 by 8. In both of these cases, like in the last slide, you can push a little bit faster. Obviously, I have personal best practice times that are significantly better than 16.2 seconds from putting in a lot of effort and then occasionally getting lucky. Okay, so what have we learned from that model and from those observations? If you are a Soroban competitor and you are using single-digit cross multiplication, you are forfeiting your Soroban advantage. There is no visualization required for single-digit cross multiplication, and so your Soroban training is not directly providing any sort of benefit in solving the multiplication question. Additionally, it is not clear. I do not believe that Soroban training necessarily produces faster times for two-digit addition. Yes, if you've practiced flash anzan a lot, you've practiced addition a lot, that will help your times. But as I showed in the addition tutorial video, top Western competitors appear to be able to add two-digit numbers at approximately the same speed as top Soroban competitors can add more numbers. Soroban training allows you to add additional columns, but not directly going to increase your speed, although if you are practicing flash anzan a lot, you will increase your speed. So Aryan, likely a little bit faster adding two-digit numbers than myself. So if we're going to use this model to estimate cross multiplication time for Aryan, well, I'm still using a 0.1 for the 64 1 by 1 multiplications, but I'm going to take the addition time and decrease it from 0.2 to 0.15, which results in 13.75 second estimate for an 8 by 8 multiplication, which again happens to be extremely consistent with his current practice times. How fast can you go using 1 by 1 cross multiplication? It looks like 10 to 12 seconds is probably the limit. I'm not sure how much faster you're really going to be able to process 1 by 1 multiplications. Maybe you can get that addition time down near 0.1 as you see in Japanese flash anzan videos where they're able to do 3-digit flash anzan practice at 0.1. So maybe Aryan can get that 2-digit addition near 0.1, which would result in a time of 11.3 seconds. Okay, so now we're going to talk about in more detail why the school method works, why it results in a faster time for multiplication questions, and what, if any, limitations there are. So both calculations, you are obviously, when you really think about it, going to be doing the same exact multiplication and addition steps. You are doing them in different order, but you're just deconstructing the question to a different extent in the different methods. But breaking calculations into the smallest discrete calculation you can is not necessarily the most efficient way to do calculations. If you think about additions, a talented Sorbonne competitor is going to try to add more and more columns, and that gives them an advantage. It is not helpful to break up a 10-digit numbers and only add them one column at a time. Even top non-Sorbonne competitors are going to do more than one column at a time. So not necessarily to your advantage to break up a question into the smallest discrete calculations. I tested this with multiplications as well, and it clearly appears to me that it also applies to the multiplication process. Despite never having practiced 5x1 multiplication in any sort of form before, when I sat down and tested, I was immediately less than 5 times the time at a 5x1 compared to a 1x1. So what does that mean? Well, I think there's a minimum reaction time there. You have to think about the new 1x1 and solve it. Whereas in a 5x1, you see everything in front of you. Your brain sort of processed the next step as it's going, separating it into discrete processes. For whatever the scientific neuroscience explanation is, it is adding time. It was very, very clear. And there's another important observation here is not only was the 5x1 multiplication time less than 5 times the 1x1 multiplication time, but when you're doing that 5x1, you're actually absorbing some of the additions that are separately classified in the cross multiplication. So for instance, in the cross multiplication, for a 5x5, we came up with 16 two-digit additions. That's adding 32 digits. In a school method, we added 4 5-digit numbers. That's adding 20 digits. So we've decreased the addition time by absorbing some of those additions into what we're considering to be multiplication time. And despite that extra work, the multiplication process is still more efficient than it was with cross multiplication. So is there a way we can make cross multiplication better? Is there a way we can use cross multiplication to reach the same times that the Japanese competitors are able to? And the answer, I believe, is yes. If we can use multi-digit cross multiplication and come up with a similar performance as what we see in the Sorbonne videos out of Japan. So if you're doing an 8x8 multiplication, 2-digit cross multiplication process is going to involve 16 2x2 multiplications and 9 3-digit additions to solve the question. Based on prior performances, we know Aryan can easily do 3-digit additions at 0.25 seconds. That is likely a noticeable overstatement of the time necessary for him to do that. But we're going to be very, very cautious for the point of making this argument, and we'll estimate it at 0.25 seconds. I tried my best to estimate what a 2x2 multiplication time is. I'm using 0.6 seconds as my best guess, but that to me is a little bit slow. I mean, we saw in the cross multiplication video, including typing the answer, a time of 1.0 seconds appears reasonable. At the very least, when we're solving cross multiplication, we can continue working on the next step while we're typing. The typing doesn't necessarily absorb time. So I do think 0.6 seconds is reasonable, but I think with practice, somebody could end up with a time that's even lower than that. So when we're putting those together, we come up with our estimate here, 2.25 seconds for the addition component, and 16 2x2 multiplications of 9.6 seconds. That's 11.85 seconds. We are already at an improvement. Again, as I mentioned before, 0.25 seconds, that is an overestimate for Aryan's addition time. So I think we're looking at more of a 0.5 seconds for the multiplications and a 0.2 for the addition for somebody who is very talented and has practiced significantly. That has resulted in a sub 10-second time, and I do believe further progress is absolutely possible, especially with the 2x2 multiplications if you have more or less memorized the multiplication table. So this is a very informal graph of Western versus Sorbonne times, and when I say Western, I really just mean cross multiplication approach. You can see at 2 by 2 down at the bottom left, it does not really appear to matter. The increase in times for cross multiplication is much more significant as we move to 3, 4, 5 digits than it is in Japan. Now, I don't have detailed time estimates for Japan for 6 by 6 and 7 by 7. Their own Sorbonne rating test only goes up to 6 by 5, so we can only glean information from single performances that are available in videos online. So after 5 by 5, it appears the increase in time for school method starts to resemble the increase in time for the Western method. And how far that it can be taken depends on the experience level and talent of the competitor. We know from videos online there are at least a few elite Japanese competitors who can do 8 by 8 multiplication at a much faster time than we can using cross multiplication. But it is true that past the 5 by 5, it appears that the visualization starts to become difficult, and it is resulting in a time that's increasing at roughly the same rate as a cross multiplication time. However, that gap is not really shrinking that much. It would probably have to become a rather significant number before cross multiplication actually caught back up. So what should you take away from this comparison, the school method and cross multiplication? If the question is within your visualization ability, school method is a superior approach. It's more efficient. It results in faster times. It's simply deconstructing the number beyond what you need to deconstruct it is not an efficient way to solve calculations. If you cannot visualize the smaller of the two numbers you're working with and comfortably continue calculating, then cross multiplication is necessary in order to solve the question. However, two-digit, multi-digit cross multiplication is clearly an improvement as long as you can say two things are satisfied. One, you can do three-digit additions comfortably, and two, you can do two-digit multiplications, 2 by 2 multiplications comfortably. Now, if you really want a really good time, those 2 by 2 multiplications, you're essentially almost going to have to know them. There cannot really be hesitancy. In general, you should have semi-consciously memorized the 2 by 2 multiplications or almost instantly know them. For 3 by 3 additions, this is also tough for non-Sorbonne competitors. Many non-Sorbonne competitors can do two-digit additions rather quickly, but 3 is rare. So you have to have that comfort level with the 3-digit additions. However, there is some basis for optimism and hope. We can see from the performances of Wenzel Gruis that this using multi-digit cross multiplication effectively does appear to be possible. Now, Wenzel does not appear to have any hesitancy or delay in solving 2 by 2 multiplications. Whether you call that having memorized them or he just knows them, he does appear to know them. 3-digit additions, he is able to do 3-digit additions comfortably. To truly use multi-digit cross multiplication in a way that would set a new record, he probably needs to get a little bit faster with those 3-digit additions and become more comfortable with the process of using multi-digit cross multiplication, building that muscle memory. But we have seen him use 3-digit additions rather productively in calculation league competitions.